Okay, so this time we will discuss about the law of radioactive decay. Okay, and before that, let's define the radioactivity. Okay, so radioactivity is spontaneous decay, or sometimes we call it disintegration. Okay, of the nucleus. Not nuclei. Better if I use nuclei. Okay, so it's the spontaneous process. It's so this is the meaning of radioactivity. So okay, so in this video, okay, we are going to deal with the quantitative aspect of radioactivity. Okay. So I begin with, let's say, okay, let's say I have okay let's say I have uh, nuclide nuclide number one. Okay. So this the ensemble of nuclide number one. Okay, nuclide number one. So decaying, okay, so decaying to different nuclide. Okay. I name it nuclide number two. Okay. So it could be okay. So as one, so if it decay, okay, I change its color. Okay, so the nuclide that has decayed, okay, is colored here. Okay, so the more time elapsed, uh, the more of the nuclide number one would decay. So the nuclide number one is called the parent. Okay. So number two is obviously the daughter nuclides. Okay, I'm worried here. Okay, I'm recording. Okay, it's okay. Full screen. Okay, so let's say if I know, okay, if I know at the beginning, there were n one. There were n. There were n 1 0. Okay, at the beginning means that time t equal 0. Okay, so there were n1, so the number of nuclide, parent nuclide is n10. Okay, and at other time, after some time, okay, at other time, let's say t, okay, there are n1t. Okay, so the number, so obvious, so logically, okay, logically because the parent nuclides spontaneously decay, okay, meaning that the number of parent nuclides will gradually okay, let's say this is time will logically decreasing. Okay, so from now on we are going to look at how the parent nuclides number of parent nuclides uh, decrease by time. And we are going to derive the mathematical formula for that. Okay, so before that we need to define we need to set up the mathematical uh, differential equation for that. Okay, so the next what we have to consider is the okay, so let's say okay, so n1t is the number of parent nuclides, okay, at time t, and so this is the number of parent nuclei at time t, okay, and with time it is uh, they are it is decreasing, okay, meaning that the number of parent nuclides is gradually reduced as the time goes by. Okay, and this reduction, okay, or can be expressed according to d and t over dt, okay, minus some constant, okay, lambda and 1, okay, and this is lambda 1. Okay, so the meaning of this, so let's call this equation number 1. Okay, so this is on the left side. Okay, so this is the rate of change, okay, the rate of change, rate of change of the number of parent nuclides at time t. Okay, so uh, it is proportional to the at time t. Okay, so the rate of change of n1, okay, at time t is proportional to the n1 at time t. Okay, so it means that the more you have the more there are the nuclides, meaning that the more the nuclides, the more the rate of change of the nuclides. Okay, so which is why uh, we have the n1t on the right side. Okay, and this proportionality, okay, is governed by a constant that we name that is lambda 1. Okay, we use lambda 1, okay, and minus indicate that the number, okay, the number of uh, nuclides is reducing, okay, as the time goes by. As the time goes by, it is reducing. Okay, so uh, so what so now no so now what you can determine from equation number 1 is the n1t. Okay, so from equation 1 we can deduce the formula for the number of parent nuclei at time t. Okay, so what you need to do is mathematically you have to integrate the equation number 1. Okay, so if you do that, okay, that is n1 d over dt minus lambda 1 dt plus integration constant. Okay, so you want to integrate it from 0 to t. Okay, 0 to t. Wait a minute, this is wrong. Okay, before you can do okay, I'm sorry, before we can do this, okay, we need some extra work. So you need to, so this is mathematical task. Okay, so you move uh n1t to the left n1t to the left, okay, and dt to the right. You do the integration. Let's see. Okay, so time from 0 to time t. Okay, and let's say at time 0, so let's say and at time 0 we know that, okay, we declared just now at time 0 the number of parent nuclides is n10. So this is n10 to time t is n1t. Okay, we don't know t can be anytime. So what is the nt at t that we are asking here? So if you solve the integration, okay, you will get uh, ln ln n t n1t to n10, okay, equal to minus lambda t plus c. t0. Okay, so if you okay, so if you solve this, okay, you get c equal to 0. Okay, and the final formula that we want is n1t equal to n10 exponential minus lambda 1 t. Okay, so let's call this equation 2. Yeah, I skip the explanation for the mathematical steps. If you want to know more, I think you can try it by yourself. So you will get equation number 2. Okay, if you try to plot this, okay, this is the time, okay, this is time 0, this is the number of parent nuclei. Okay, so it should start with n10 here, okay, and it will exponentially decrease. Okay, and that's how that is this is the relationship between the number of parent nuclei with time. Okay, so that this is merely the number of uh, parent nuclides. Okay, with time, it is decreasing. So next is the main theme, okay, for this video, which is the radioactivity. Okay, so radioactivity, or simply people call it activity, okay, is the number of decay per unit time, okay? Or R equal to, mathematically, is the nt over dt. Okay, so this is the definition of radioactivity. So we know the nt for the parent nuclide. Okay, so the radioactivity, the radioactivity by the parent nuclide, okay, is the modulus of the differentiation of n1t with respect to t. Okay, so if you do this, okay, if you put equation number 2, okay, you will get exactly lambda 1 and 1 0 exponential minus lambda 1 t. Okay, so let's call this equation number 3. Okay, and if you see, okay, if you take a look at this part, okay, this part is actually question number 2. Okay, so radioactivity, okay, radioactivity of the parent nuclides is equal to its the lambda 1, the lambda, okay, lambda 1 has a name, I forgot to mention here. Lambda 1 is called decay constant. Okay, lambda 1 is called decay constant. Okay, specific for the parent nuclides. Okay, so lambda 1 and 1t. Okay, so if you ask, if t, so if at time t equals 0, so the r0 will be lambda 1 and 1 0. Okay, and rt, so at any time t, okay, it is equal to lambda 1 times n1 t. Okay, n1 t is what we had here according to equation number 2. Okay, and okay, and as the nt, okay, as n1 t decrease exponentially with time, okay, so you find that r1t also will decrease exponentially with time. Okay, um, it's a bad example. Let's use better example. Okay, since we know the r0, okay, r10, okay, so this is at this point it is precisely equal to r10, which is equal to lambda 1 and 1 0. Very sorry, apologize. Yeah, I should draw it bigger. Okay, so is T equal to 0. This is the activity. Okay, so at time 0, the activity is exactly R10, which is lambda 1 and 10. Okay, so because it is governed by this exponent, by the exponential term, okay, so you get the same pattern as for the n 1t. Okay, so it decreases exponentially with time. Okay, and what else? Hmm. Okay. Uh, I think that's all. It's all for now. Okay, so next, okay, so next, let's think about half-life. Half-life is the time that the radioactivity become half of the initial uh, radioactivity. Okay, or if or the number, or other than radioactivity, you can consider also the number of nuclides. Okay, initial number of, okay. So meaning that you can use equation 3, okay, or equation number 2 to derive or to reduce the half life. And before that, okay, now I remember. Now I remember the thing that I forgot. Yes, now. Okay. You can see, you see now, R10 is equal to lambda 1 and 10. Okay, so R1t, okay, can also express as now you see this part. Okay, that part is exactly equal to this relationship. Okay, so R1t is equal to R10 exponential minus lambda 1 t. Okay, so so okay, so knowing the initial radioactivity, okay, and the decay constant of the nuclides, you can calculate the present radioactivity of the nuclides. Okay, that's the conclusion. Okay, and this one means that knowing the initial number of the parent nuclide and the decay constant, you can deduce, or you can calculate the present number of the parent nuclides that hasn't decayed yet. Okay. Okay, now let's continue to the half-life. Okay, so if I choose equation number 2, okay, number 2, which is the n 1t equal to the n 10, okay, initial number of the parent nuclide at time 0, minus lambda 1 t. Okay, if I choose this, you can also work with equation, let's say this is equation number 4. Okay, you can also work with equation 4 as well. So if you choose to consider the number of nuclides, okay, then use equation number 2. Okay, so the time, okay, so let's say the time, okay. So if the initial number of radionuclide is n 10, okay, so its half, okay, its half is n 10 over 2, okay, and the half occur exactly as the time equal to the half-life. Okay, half-life is t1 over 2. Okay, this is the notation for half-life. Okay, and so what exactly is t over 2? If you work with the equation, okay, you will find that t 1 over 2 is ln 2 over lambda 1. Okay, so this gives us the relationship between half-life and the decay constant. Okay, and ln 2, if you punch your calculator, you get 0.693, okay, over lambda. So this is, let's say this is equation 5. Okay, we call this equation 5. Okay, so after, let's say at t0, at time 0, okay, and 10, okay, so the initial number of nuclide is n10, okay, so after one half-life, okay, it become n10 over 2, it become half. Okay, as the definition of half-life is that the number of nuclides reduced by half. Okay, so after 2 half-life, it further reduced by half, so you get n10 over 4. Okay, after 3 half-life, 10 over 16. Oh no, not 16, over 8. Okay, this one divided by 2, you get it. You get n10 over 8. Okay, the story can be continued if you want. Okay, and what is the meaning? Okay, what is the meaning of decay constant? Decay constant carries quite important meaning. Okay, if we go back here, okay, here, let's use different color. So if I put the decay constant alone, okay, from equation number 1, it becomes minus n 1t over dt over this is wrong. Okay, over dn1 t, okay, over 1 multiply with 1 over dt. Okay. So this is the uh this term, this part is the probability of decay. So n1 t is the n1 t is the total number of nuclides at time t. Okay, but dnt shows the change, the decaying, the number of decaying nuclides at time t. Okay, so the ratio, okay, is equivalent to the probability of decay, okay, at time t, and dt is uh, unit time. Okay, this is by dividing this part with dt, which is the unit time. Okay, lambda, the decay constant, is the meaning of decay constant is the probability of decay per unit time. Unit time. Okay, so that's the meaning of decay constant, our decay constant lambda. So if lambda, the bigger the lambda, means that the more decay is occurring. Okay, that's the meaning of decay constant. So next, okay, we discuss the decay constant. Okay, discuss the unit of activity. Okay. Let's go back to the rate. Let's use rate. Okay, unit for the activity. Okay. The old one is Curie. The symbol is CI. The SI unit is becquerel. Becquerel. Okay, the symbol is BQ. So 1 BQ means 1 decay per second. Okay, and for the all unit Curie, 1 Curie equal to the 3.7 10 to the power of 10 decays per second. Okay. So the in we can conclude here is that 1 curie equal to 3.7 10 to the power of 10 becquerel. Okay, so that's the first part. Okay, the second part, okay, we need to think, okay, the decay, okay, the decay of parent nuclides, okay, does not necessarily end up and at decay at the and at decay nucleus. What I'm trying to say here is that one decay becoming two, and after that, and two is the stable nuclides. Okay, so that is not always the case. It could be the parent decay producing daughter, okay, and the daughter further decay becoming a granddaughter. Okay, so this is parent, daughter, this is uh, granddaughter. If you can continue, then you will have granddaughter, daughter. Okay, so you can continue until finally the ground state or the stable nuclide. Okay, so now I want to consider. Let's consider. So the previous example, we consider the what happened to the number of parent nuclides with time. Okay, so now let's think about the number of daughter nuclides. Okay, if it also decaying, okay, producing a granddaughter. Okay. So uh, now think about daughter nuclides. Okay, the rate the so in a statement, okay, the rate of change of daughter nuclides, okay, equal to, okay, so the daughter nuclide born from parents, okay, born from the decaying parent. So the amount of decay of the parent now become the amount of the daughter. Okay, so because the daughter is born from the parent, from the decaying parent. So it is the rate of change uh, no, not rate of change, it's supposed to be rate of production of from A, from parent, from the parent. Okay, I better I write it nicely. Rate of production from the parent, okay, and at the same time, uh, daughter nuclides is reduced because it turning itself to granddaughter. Okay, so this is, so you have to deduct it with the of change rate of change or rate of uh, decay. Better use rate of change of 2 to 3. Okay, so this, the rate of progression from 1 is equal to the rate of decay of 1. Okay, so that is in, let's call this equation number 6. So that's the statement. Okay, and mathematically, okay, uh, the dn2 t over dt equal to uh, lambda 1 and 1 t minus lambda 2 and 2t. Okay, and you can use n1t from equation 2. Okay, equation 2. So lambda 1 and 1 0. Okay, exponential minus lambda 1 t. So minus lambda 2 and 2t. Okay, and with condition, and then you, what you have to do, okay, like in the previous explanation, you're going to integrate the equations. Okay, if you do so, okay, mm, let's call this equation 7. So integration of 7 with initial condition and to 0 equal to 0. Okay, you will get no you get uh, we get and to t, which is equal to the mathematic is very long. Okay, so I skip it. If you are interested to know the mathematic, you can search it by yourself. So it become lambda 1 over lambda 2 minus lambda 1, okay, and 1 0 exponential minus lambda 1 t minus exponential minus lambda 2 t. Okay, so this is the uh, number of uh, the daughter nuclides, okay, as the time goes by. Okay, so if you okay, and similarly, okay, so the r2t equal to like the R1T. The R1T is this one. Okay, R1T is decay constant 1 multiply with the N1T. Okay, so R2T is lambda 2 multiply with N2T. Okay, so you get lambda 2 lambda 1 over lambda 2 minus lambda 1. Okay, remember N2T is here. Okay, so become this one minus A minus E. Okay, so this is the activity for the daughter nuclides. This is the number of daughter nuclides. Okay. And if you plot on the same graph, okay, there is T. This is the N T. Okay, so you will this is not zero. Okay, we don't fix that zero. Okay, to make our discussion easier, this point is not necessarily zero. So roughly, okay, this is the N1T. Okay. Same with this figure. Okay. So this is N1T. Okay. And N2T, okay, N2T will look approximately like this. So it increase and then it decrease. Okay, why it is increase at the place? Because more daughter nuclides are produced from the decaying parent nuclide. So it first increase, okay, and then it decrease. Okay. And you can find the what is the time when the N to T become maximum. Okay. By okay, let's call this equation 8. Okay. This is equation 8. This is equation 9. Okay. If you differentiate 8, okay, and equal it to 0, you will find T, which is the T max. That is the T max, which if mathematically it is 1 over lambda 2 over minus lambda 1 ln lambda 2 over lambda 1. Okay, so before this T maximum, okay, the number increase exponentially, but after that it decrease exponentially. Okay. Okay. Before the T max, okay, it doesn't mean that the daughter is not decaying. Okay, it is decaying, but the rate of production is greater. Okay, from before the T max, the rate of production of N2 is greater than the rate of decaying of N2 to N3. Okay? So it appear increasing. Okay, and after that it decrease. Okay, so the same pattern. Okay, the same pattern you can get for the R, for the activity. Okay. That is the R T, and this one is R2 T. Okay, and this is the T max. So that's the story. If so, that's the story. If you if that's on the so up to this point, okay, we discuss N1 and 2. Okay, you can also repeat the same procedure. Get N3 and 4 and until we don't know, let's say Ni. Okay. Let's say Ni. Okay. And you can see as you go further, okay, the amount of the uh, parameter in the equation will become bigger, become larger. Okay, and uh, if you analytically want to reduce it, you can do it. Okay, but it will be very tedious, a very tedious job. Okay, to do. So in uh, in summary, okay, in summary, if you the pattern will be the same. Okay? The pattern for the question will be the same, and finally, okay, eventually, if you perform uh, the calculation for n3 n4 n5 and so on and so on, okay, you will come out, okay, with general formulation. Okay, let's say ni. Okay, ni is something in the middle here. Okay, I can be any integer number, positive integer number. So you will get ni equal to lambda 1, lambda 2. Okay, multiple you go continue up to 1 lambda before I. Okay, I minus 1. Okay, and 1 0. Okay, and in the bracket, okay, in the bracket you get the exponential minus lambda 1 t, okay, over lambda 2 minus lambda 1. Okay, and then uh, lambda 2 lambda 1 lambda 3, next is lambda 3 lambda 1. Okay, until lambda I minus lambda I minus 1. Okay, plus, okay, and plus exponential minus lambda I t, okay, over lambda I lambda 1 minus lambda I minus 1 minus lambda I. Okay, so this is the general formula for any for any stage at any stage. Okay, be it 2 3 4 or anything, okay, that represented by I. Okay, and I think that's it. Okay, that's the conclusion for this derivation of number of nuclides, okay, by time. Okay, as the time goes by, what is the number of nuclides? So as the radioactivity of the nuclides. Okay, you can try. Let's say I is 3. Okay, so n 3 t equal to uh, lambda 1 until lambda 2. Okay, and 1 0. So in the bracket, it is d exponential minus 1 t over lambda 2 minus lambda 1. Okay, lambda I is 3, so lambda 3 minus lambda 2. That's the first term. Okay, second term is e exponential not exp, it should be e. So e minus lambda 2t over lambda 1 minus lambda 2 lambda 3 minus lambda 2. Okay, plus final term e minus lambda 3t over lambda 1 minus lambda 3 lambda 2 minus lambda 3. Okay, so if you want to continue I with 4, you can do it. Okay, but that's how you can easily calculate the n for any I. uh, so okay. So mathematically okay, uh, for I is equal 3, lambda 1 cannot be equal to lambda 2, cannot be equal to lambda 3. Okay, this is the prerequisite for the calculation of n3 in this example. Because why it is so? Because if they are equal, then the denominator will become 0 and spoil the whole equation. Okay, so next is there are two special cases which is called transient equilibrium. Yeah, let's think about the parent decaying to daughter, and the daughter further decaying to granddaughter. In the special case, this is special cases. Special case number 1, which is it is called transient equilibrium. Equilibrium. Okay, so what is transient equilibrium. It occurs when the decay constant of the parent is far 10, it is 10 to 10 times, okay, smaller than the daughter decay constant, meaning that the half-life of the parent, okay, the half-life of the parent, I so I'm going to use this notation, okay, bracket 1, okay, t 1 over 2 in bracket number 1 is the half-life, is to show the half-life for the parent, half-life for the parent, okay, so meaning that the half-life of the parent is far greater than the half-life of the daughter. Okay, maybe I should remove bracket, the outside bracket here. Okay. Okay, S T1 over 2 equal to the ln 2 of lambda, okay, the decay constant. So the smaller the decay constant, the greater the half-life. Okay, so now in this case, the parent has a smaller decay constant, so its half-life is bigger, okay, than the daughter. So in this case, okay, the number of daughter nuclides, okay, which is we did it as in the equation number 8, okay, lambda 1 over lambda 2 minus lambda 1 and 1 0 exponential minus lambda 1 t minus exponential minus lambda 2 t. Okay. So this can be approximate. Okay, as the as lambda 2 is bigger than lambda 1. Okay, so meaning that this term can be can be considered as to be nearly equal to 0. Okay, so we can neglect this the second term. Okay, so leave us with lambda 1 over lambda 2 minus lambda 1 and 1 0 exponential minus lambda 1 t. Okay, and further, I hope you still can follow. I hope you still can follow the discussion. Okay. The ratio, okay, the ratio of activity of the daughter to the activity of the parent, okay, is this is lambda 2 and 2t, okay, this is lambda 1 and 2 1, okay, and so lambda wait a minute, and no, this is n1 n1 lambda 1 and 1. Okay, so then okay, lambda 2 is lambda. Okay, so the numerator is lambda 2 n to t. Okay, so n to t is this one, lambda 1 over lambda 2 minus lambda 1. Okay, and then n 0 exponentials minus 1t. So that's account for the numerator, and the denominator, okay, still there, which is lambda 1, okay, times n1t. Okay, and if you still remember, n1t is n10 exponential minus lambda 1t. Okay. What can we see here? Okay, what can we see here? This one vanish. Okay, and leave us with okay, I need to add more pages. Okay, leave us, so the ratio of a2 over a1 is about approximately lambda 2 over lambda 2 minus lambda 1. Okay? And as lambda 2 is bigger than lambda 1, okay, this ratio is positive, okay, or is greater than 1. Okay? So if you have, if you know, if you happen to know that the activity of this is the why I use a, it is not a, I'm sorry, it is r. Why I use a, supposed to be r. Okay, I'm sorry, it's not a, this is supposed to be r. Okay, for activity, okay, this is for activity. Become messy now, so this is activity, okay, r, not a, r. So this one should be r2, the r1. Okay, so if you know, if you you know, r1 is according to this curve. Okay, that is r1 t. So this is t, this is rt, and as the ratio of r2 over r1 is uh, greater than 1. Okay, so r2, okay, is about something greater than 1. Okay, something is greater than 1. Okay, multiply with r1. Okay, so on the same graph, okay, same graph, r2 will follow r1, okay, after uh, some time, okay, after about 2 half-life. Okay. So this is r2, the activity of from the r2 is will follow the activity of r1. This is the case that we call it transient equilibrium. Okay, after some time, the activity of r2 and r1 is nearly equal. It happen if the decay constant of the daughter is bigger than the parent. Okay, about 7 to 10 times bigger. That is the transient equilibrium. The second special case, I think special case number 2, special case number 2 is called secular equilibrium. Equilibrium. Okay. This occurs when the daughter nuclide has a far bigger decay constant than the parent nuclide. Okay, so the half life of the parent, okay, is way bigger than the half life of daughter. Okay, so in this case, okay, let's continue with this relationship. Okay, so R2, T ratio of R2 over R1 T, okay, was lambda 2 over lambda 2 minus lambda 1. Okay, now in this secular equilibrium, as the lambda 2 is way bigger than lambda 1. Okay, so lambda 1 can be neglected. Okay, so lambda 2 lambda 1, wait a minute, lambda 2, this is okay. Now okay, so this can, okay, so this lambda 1 is smaller than lambda 2. Okay, so we can neglect lambda 1 at the denominator, so you end up with lambda 2 over lambda 2, which is 1. Okay, so as the this is T, okay, this is RT. Okay, so in this case, since because the half life, because the half life of lambda 1 is way bigger than uh, the half life of the daughter. Okay, so if it is on the same scale, it is on the same magnitude of time scale as in this figure. Okay, so the parent, okay, the parent activity will appear as will appear flat, okay, flattening. Okay, if you look, but of course, if you look at the bigger or at the longer time scale, it will decrease. Okay, but on the short time scale, okay, it will appear a straight line. Okay, and for the parent, for the activity of the parent, and from this relationship, okay, you can deduce that the daughter, the activity of the daughter will also follow the activity of the parent. Okay, so two will increase, and after some time it will follow exactly the same as the parent. Okay, so this is R2T. So this is the special case number 2, which is called secular equilibrium. Okay. So that's I think that's the end of the uh, law of radioactive decay. Okay, I know this is difficult, so please repeat a few times so you get a deeper understanding about the mathematics and also the principle that we discuss here. Okay. So if you have question, so this is not yet okay for those who in my class. Okay, so this is not yet the end of the chapter 4. Okay, we still have to cover uh, activity, specific activity. Okay, we cover activity, but not yet specific activity. But this is simple. Okay, and decay chain we have covered here. Okay, so this topic is supposed to be uh, decay, law of radioactive decay and radioactive decay chain. 4.5 active decay chain. Okay. So those following my class, next is the topic that left are the natural radioactivity and the specific activity. Okay, that's all. Okay, so please study. If you have any question, leave. You can text me or leave the question under the section down below. So that's all. Thank you.